In this video, we'll continue looking at a charging RC circuit. We produced a set of graphs, one for the charge on the capacitor, one for the voltage on a capacitor. And you'll notice that these graphs in the last video looked alike. And that's not by chance. They must always look alike. This is because they're related by the fundamental equation defining capacitance. The charge on the plates depends on the capacitance times the voltage across the capacitor. So, because of this relation, Q and VC graphs always look alike. That's what the definition of capacitance tells us. So, on an AP test or exam in a class, if you happen to be seeing a choice, say on a multiple choice of different graphs, these graphs not only have to be continuous, they can never have jumps, but they have to look the same. The only thing that changes is that the height of this graph is multiplied by the value of C to get the height of the graph for the charge. Likewise, if you look at the current through a resistor and the voltage across the resistor, those two graphs have to look alike. And that's because VR is equal to I times R by Ohm's law. So I and VR graphs must look alike. Now you'll notice that the current and the voltage across the resistor graphs are not continuous. They have a jump discontinuity. They go from here up here. A very short period of time. Now in reality, they probably don't exactly, if you measure them small enough, have an exact jump. But it's very, very steep discontinuity there. And so the reason for that is that in the case of the capacitor, it has energy. And it takes time to move energy. If you move charge or change the voltage, you change the energy of the capacitor. And I remind you that the capacitor's energy, for instance, U on a capacitor is proportional to 1/2 CV squared. So if you change V in no time, you change the energy in no time. But the power would be equal to the energy over the time. So if you changed energy in no time, it takes an infinite amount of power. And you don't have, and nothing in the world has, an infinite amount of power. In the case of the resistor, there is no energy stored. The resistor uses up energy. So it can have the current and the voltage change, because that doesn't mean an infinite power. It's not energy. The current times the voltage is the power it starts to use. So in this case, for instance, I would have E squared over R. That is the battery. If it was 4.5 volts, 4.5 volts squared divided by the resistance would be the power it was now starting to use. And in no time, it had used no energy yet. Very different. Energy is stored in a capacitor. Power is dissipated in a resistor. It's not stored. And that's why its graphs can have these jumps. Alright, that covers the basic ideas about charging a capacitor. We just need to now get some formulas for these graphs, and that does require some mathematics. Now, it turns out this graph kind of looks difficult to see for most students, while the graph down here, those they might recognize. This graph is an exponential graph. It can't be a 1 over, say, t graph, because if it's 1 over t, at 0, it would go to infinity. A 1 over graph looks something like that. It can't be a straight line. It would go below the axis. So, if you think about it a little bit, you probably figured out that this graph is an exponential. And it looks something like e to the minus t. Now there's a problem. The exponent here can never have units. And that's because an exponential is in fact an infinite series. And if that series terms, which are at different powers, had units, then you'd be adding things that had different units. And that's not allowed. So this thing here has to be multiplied by some quantity that eliminates this time. The usual way to do that is to put a constant underneath, called tau. It's a constant, and it has to have the units of a time that cancels that t. Hence, it's called a time constant. Now, we'll come back in a minute and figure out what it is that tau has to depend on. This quantity here has no units, and yet it's representing a current. So it has to have a current in front to give it units. Now, if you put 0 in here for time, the exponential e to the minus 0 would be 1. So this quantity has to be the current right here when this problem starts. We call that e sub 0. So that's this graph. This graph over here would look the same thing. It would be VR0, which would happen to be this epsilon of the battery, times e to the minus t over tau. Then the question is, what about the graphs above? Well, if you look carefully, for the voltage graph especially, you'll see that what we've done here is had this battery, this epsilon that goes all the way across, and we've cut out the curve for the resistor. This graph right here. That, if you flip that upside down, has been cut out of this E. Well, that's really just a restatement of Kirchhoff's law. So this is like E, but then we subtracted out this voltage, which was again E to the minus t over tau. Well, you can factor the E out. So it looks like 1 minus e to the minus t over tau. Where this is the maximum voltage across the capacitor, or put another way, it's VC infinity when it's fully charged. Likewise, this has a similar formula. Q would have to be equal to Q at infinity times 1 minus e to the minus t over tau. So those are the fundamental equations for finding these graphs. But notice that we got the graphs without doing any of that math. Now, there are more rigorous ways if you have calculus and such to get these, but at least at the trig level, these are generally have to be memorized. Let's talk about tau. Tau is called the RC time constant. And it's called that because its value is found by multiplying the resistance times the capacitance. If you look at the units of this, this is an ohm. And this is a farad. But a farad is equal to a second per ohm. So when you multiply by ohm, you get seconds. Now, why is this? Why is this important result that you need to memorize? Think about the capacitor by the swimming pool analogy for a minute. If it was a swimming pool and you were filling it up, and let's say you had a single size pipe and you had that swimming pool while your friend had this swimming pool. This pool has a larger C, a larger capacity. It will take more charge to raise it to the same height as the smaller pool. So it will take a longer time to fill it. Make C bigger. It takes a longer time to fill that pool. In the same way, a larger capacitance takes more charge and therefore a longer time to fill that capacitor to the same voltage. Now, what's the resistor? Well, pipes, there's a pipe, small pipe, big pipe. The big pipe can send out a lot more water. People say it has greater conductance. That means it has a small resistance. Not radius. I'm not talking about radius. It's a small resistance. The small pipe has a large resistance to water flow. Therefore, it sends out water in a slower time. If you use a small hose, it will take longer to fill a swimming pool than if you use a big hose. So a big R, which represents a small hose, means it's going to take longer. A big R means the charge finds it harder to flow through the circuit, so it takes it longer to fill up the capacitor. So take the resistance in the circuit, multiply by the capacitance, and that gives you the time constant. Now the time constant tells you how long it takes for this to go down by e to the minus 1, or this one to go up to 1 minus e to the minus 1. And that turns out that this is a little more than 30-something%, and it's a little bit less than 70%. Okay? It is a way of looking at this circuit that you could use it as a timing element, and you can. So people adjust the resistor and capacitors all the time, these RCs, in order to use this as a timing mechanism for all sorts of neat circuits. All right, I've worked out a problem for charging and discharging a capacitor on another video. This finishes the capaciting theory. You should go and watch the other video to practice the actual calculations. I'll see you on another video.